Welcome to this video which contains coding tips for my policy gradient labs. So in this video I will just provide explanation about the code of my basic policy gradient labs. This is definitely a video which is intended for my students when they will have to do these labs. You may be interested in this video if you are using my GitHub repository to code these labs by yourself, but otherwise you won't draw many messages from such a video, so just use it if you want to code. So the GitHub repository associated to the video is here, and the code is based on PyTorch. Let me say that I won't provide any explanation about how to use PyTorch, so there won't be explanation about what's happening under the hood when you call PyTorch functions. There are only a few general takeaways for those of you who are not interested in coding for those particular labs, which are explanation about gem wrappers and some general explanation about how to use hyperparameters as arguments when you are coding reinforcement learning application, for instance. So about the content, I will tell you about policies, I will tell you about critics, I will explain you how you can represent the data with episodes and batches or with PyTorch datasets. I will provide you explanation about the gem wrappers, the general idea of gem wrappers and the specific gem wrappers I coded for those labs. I will tell you about the kind of value visualization that you can obtain with these labs, and then a few general classes, among which the argument part. So let's start with policies. Here you have a general view of the classes that are used to represent policies, and let me say that the generic net class here is also useful for the critic, which are also neural networks. Okay, so you have generic net. So a generic net is used to represent any neural network, and what's important is that you can save and load a neural network. Okay, and in fact the policy wrapper uses this capability to save and load a generic net using those functions. And for those of you who are doing the labs in the context of my classes, you will need to use these policy wrappers to save the neural network you have obtained on a particular benchmark, so that I can reuse the network you obtain to see what's your performance. Okay, so the generic net, you have the policies and you have the critic, and you will see that there are three kinds of policies that are provided. There is the Bernoulli policy, the normal policy, and the squash quotient policy. This will be explained just after that, and that's in the policies folder. You might have different kinds of policies, such as convolutional neural networks policies, etc., but that's the three that I have in the code. And you also have different kinds of critic. So there is a general critic network with a few methods like update with temporal differences and update with Monte Carlo. And then there are more specific type of critic networks, so a value network, a queue network with discrete actions, and a queue network with continuous actions. So let's start with different kinds of policies. So what's a Bernoulli policy? That's also explained in my policy search class. So a Bernoulli policy has a binary output, either 0 or 1, and whether it will provide a 0 or 1 is based on a probability. So you draw a number between 0 and 100, and if you are below the threshold, then you will output 0, and if you are above the threshold, you will give a 1, or the contrary. Okay, so that's how it is coded. So you have the Bernoulli policy class. It inherits from generic net, as I said. So to initialize those network, in fact, you have to give the size of the different layers. Okay, so for instance here you will give 200, 200, and 40, and then 10, for instance, and you have to give a learning rate. And as you can see in the initialization function, you describe the different layers. Here we are using linear layers mainly, and then you choose an optimizer. Here I have chosen to use RMS prop. It could have been Adam or anything else. Okay. Then in all those classes, your policy and critic classes, you have a forward function. Okay. So what's the policy? You take as input a state and you give an action. So the forward part just transforms the state into torch vector, tensor in fact. Then it propagates the input up to the output layer, and here what you will get is a distribution of action. So you will use a sigmoid to determine what's the value of the threshold, and then you output this torch value. And if you want to use rather a vector or a number, then instead of calling forward, you will call select action. You also give it the state. It calls forward, and then it gives you a specific action by calling on the Bernoulli layer, okay, PyTorch layer, sorry, and then sampling from this probability distribution and transforming the chosen action into an integer. Okay. That gives you a general idea of how we use those policy classes. And here you have an example of how to train a policy. So here you give it a state, an action, and a reward. Okay, that's a sample that you have in your replay buffer, for instance. You transform them into PyTorch tensors. Then you use the forward to get the probabilities. Okay, in fact, I have called this action. It should have been probability of action, because what you get is probabilities when you call a forward. Then you call on the Bernoulli layer so as to transform that into some binary choice. And the loss will be the log probability of your action minus times the reward, and you take the negative of that. Okay, so that's the negative score function times the reward, and you will update your network using self.update, that's PyTorch, with this loss, and this will train your actor. Sorry. Different kind of policy is the normal policy. So what's a normal policy? That's a policy that has a Gaussian distribution instead of a Bernoulli one. And it's using the normal PyTorch distribution class. Okay. So this can be used to output a continuous action between, for instance, -1 and 1 here, and you will have a higher probability to take the action corresponding to the center here. One point is that the integral must keep to 1, and you may either adapt the variance here to have a more peaked or a less peaked Gaussian or not. As you will see in the code later on, we will switch to from one case to the other one. Okay, and then you can. So okay, I just said that you can just keep the variance constant or apply gradient descent also to adapt the variance. So here is how it is coded. So you can find the same functions as in the Bernoulli class, and here there is this point about here I am using constant variance. In fact, that's the standard deviation which is constant. Okay, and it's explained in my practical policy gradient video why I moved from using some adaptive standard deviation to a constant one, because if I was using this, then the initial standard deviation was too small, so the policy was not exploring much, and by doing this I get something that works in practice for the CART-POL benchmark. Okay, and the rest is very similar to the Bernoulli policy, apart from the fact that to get an action I am using the normal distribution instead of the policy distribution. Okay, but the rest is very, very similar. And finally, you have the squashed Gaussian distribution. This slide is taken from my soft actor critic video that you can find also on my YouTube channel. And that's very similar to the normal distribution policy. The difference being that on top of this normal policy, we add a hyperbolic tangent function so as to squash the output between here -1 and 1. Okay, and if you do this, then the way to compute the log probability is a little more complicated, as you will see immediately in the code, and I won't explain again all these details, but as you can see in the squash Gaussian policy Python class, you have a function which helps you compute the log probability of an action given a normal distribution, and the calculation is given here. You can find the explanation for this calculation in spinning up on, okay, that's taken for this code, and in this code they tell you in which paper you should have a look to understand these calculations. Again, you have an initialization. In that case, I decided to use Adam, but it could have been RMS prop too. That's the same. And the select action function is a little more complicated, okay, because there are two cases. You can use the squash Gaussian in a deterministic case or in a continuous, okay, in a stochastic case. And for training your function, you have to use the log probability function that I have defined before. Okay, again, I am not going into the details too much. This video is just intended to give you an overview, and then you have to go into more details by yourself if you want to get the details of the code. And then, as I told you when presenting the general hierarchy of classes, you have the policy wrapper class, which is used to save a policy to a file and load it from a file, and this is used by the evaluator when I will ask students to get policies by training them using the labs, and the evaluator will get those policy files and rank them according to their performance given a particular benchmark. Okay, and the file name itself contains information about the environment, the authors, and the time limit used in a specific run to get that particular policy. And these informations are used by the evaluator just to display who was the author, what was the environment, etc. Okay. If you want to know more about this part, you should have a look at the PDF file where I am describing the goal of the lab that my students have to go through. Okay. Sorry, so a word about critics. I already explained to you this hierarchy of classes. Okay, so I don't go into the detail. This is very similar to policies. But the functions to train them, this is not train policy gradient. You have update with temporal differences and update with Monte Carlo. And again, if you want to understand this in detail, you have to watch my classes about reinforcement learning in general and policy search in particular, where those two approaches are explained, and also the video about practical use of policy search methods. Then a different part is about storing data in replay buffers. So for doing this, I have defined two simple classes, which are episodes and batch. So first, those things store samples. So what is a sample? That's the conjunction of the information an agent gets from one state, so from one step. So in one step, you are in a state, you perform an action, you get a reward, and then you end up into a next state, and those four information define a sample. Okay. An episode is just a list of samples, and a batch is just a list of episodes. And in those episode and batch classes, you have a method to add a sample to an episode and to add an episode into a batch. That's straightforward. Then you have methods to transform the reward of all samples in all episodes, and this is used to perform various policy gradient calculation. If you go back to my policy gradient class, you will see that you have a trajectory, and then you can change the reward along this trajectory in different ways. So you can just use the sum at each step, so you just sum the rewards over the whole trajectory, and you are putting the sum into each sample. So instead of the reward here, you will just have the sum of the rewards over the whole trajectory. You can either use a discounted sum, so that's the case where you perform a sum, but the rewards are discounted by a factor gamma, so gamma, gamma square, etc., etc. You can also subtract the baseline to those rewards. That's the case where the baseline is provided by a critic. This is why you need critics in those policy gradient labs. You can eventually use the n-step return. I will say at the end of this video that this part probably does not work at the moment. You can normalize the rewards, you can normalize discounted rewards, you can exponentiate the reward, etc., etc. No, there is no etc. This is just a list of methods that you have. Okay, and in the batch class, you also have the methods to train a policy or a critic from the batch, and those methods themselves will call the train PG method on the policy class, or the update Monte Carlo or update TD methods in the critic class. If you want to know more about the difference between training critic with a Monte Carlo approach or with a temporal difference approach, again, have a look at the companion video where I explain how to use policy gradient in practice. That's explained here. And here you have a link to that video. A word to say that this approach with episode and batch is something that I have done by hand, but if you are using advanced tools in PyTorch, you can use PyTorch datasets. That's a very useful set of classes to deal with data in general that are a lot used in deep learning. Okay, that's a useful set of classes to deal with datasets. It allows you to build a dataset from different sources. It allows you to very easily sample from a dataset and to, for instance, separate between a training set and a validation set and sample either from the training set or the validation step, depending on what you are doing, etc., etc. So it allows you to design high-level algorithms without having to care about details which are provided by the dataset classes. Okay, so that's an alternative to my episode batch classes. And in the code of the Policy Gradient Lab, you have both approaches. You can use either the batch or the dataset approach. Both approaches are cohabitating in the repository. This makes the code a little more complicated because, okay, you have two approaches. I suggest, particularly if you are a beginner about reinforcement learning, that you just use batch. Because this part is easier to understand. Okay, there are less mysterious functions which are hidden in the dataset class. Okay, but if you want to become an expert, you should try to use datasets because that's background coding knowledge for people who are doing machine learning. Okay. For instance, as I said, random sampling is straightforward with datasets, whereas if you want to implement random sampling from episodes and batch, then you will have to code complicated functions for that. Okay. So let's move to an interesting part, which is the gym wrapper approach. Okay. So in these policy gradient labs, we will use OpenAI gym environments to test the reinforcement learning algorithms. So those gym environments, this is for instance cart pole, mountain car, etc., etc., continuous mountain car, pendulum, there are many, okay, and you can find them on the OpenAI gym website. So gym environment is a specific class corresponding to an environment, and it provides a few methods, and the most important one being reset and step. So what's a wrapper? In fact, that's a class which is around this environment and which is also an environment. So this is very similar to the decorator design pattern for those of you who know about software engineering. So the idea is that a wrapper environment is an environment which contains an environment and which behaves as an environment. And the interesting part is that you will use the wrapper as an environment, so you will also call on reset and call the step function giving a state and getting an action. So the arrows are on the wrong side. Sorry. But the idea is that in these methods you can perform additional treatments. So you can do more things. Okay. So you will, for instance, call a reset, but here you will do something else, and then you will call the reset of the contained environment. The idea is that those transformations can be applied in between, so that they are not seen in the external code. From the external code, you are just calling reset and step of an environment as you would do with the initial environment. But here you are doing something else which is not visible in the main code. Okay. And what's interesting is that since a wrapper is an environment, a wrapper can contain a wrapper, which can contain a wrapper, which can contain a wrapper, etc., which contains finally an OpenAI gym environment. And this way of coding is often used by libraries who develop some code, some reinforcement learning code. So now I will show you a small list of the wrappers that I am using. So the first one is the action vector adapter. Okay, so as explained here in the comments, in gym environments you have some that take just a scalar action, some who take a vector of actions with several dimensions, but you also have environment which just take a vector of one action. Okay, and this action vector adapter is just meant so that you can use all one-dimensional environments with just a vector, and finally they will be called with the scalar. So you can see the details here. In fact, you give it the action which is a vector. From this vector you take the number which is in the vector, which is the action, and then you send this action to the internal environment. Okay, so you have taken a vector, you have transformed it into a number, and then you call your environment with this number, and you can see that you call the step function and it calls the step function on the same environment. So that's the spirit of the wrapper way of coding. And then by doing this, I just have to wrap environments which take a scalar so that they take a vector, so that all my environments will finally take a vector as input. Okay, that's a way to make my code more general for any environment. This one is interesting too, so that's the feature inverter wrapper. The idea is that the environments provide you state features in a particular order, and that's coded in the environment, so you cannot change that. Okay, otherwise you would have to change the code of the gym classes. But in some examples you would like to provide displays with the first two features, and the first two features are not the one that you want to visualize. So what can you do? You can change the order of the features so that the first two are the ones that are of interest to you. That's what the feature inverter is meant for. So the idea is that you will tell him which feature you want to invert, and it will, the external environment will have the feature in your order, whereas the internal environment will have the feature in the OpenAI gym order. Okay, so I'm just saying that I want to invert feature F1 and feature F2, and then when I am calling step, it just exchanges feature F1 with feature F2 in the state. And okay, so you call the action, it provides you the states in the internal environment order, and then you exchange the order and you put the exchanged order as output of your step function, so that, for instance, when displaying, you will visualize what you want. You will see an example with the cart poll case in the visualization part, or in my policy gradient in practice video. And I'm doing exactly the same for reset, so that you get the state after reset in the right order. Okay. The binary shifter is also quite useful. In fact, in many environments, you just have two actions which are -1 and 1. But a Bernoulli policy will output a 0 and a 1. So the binary shifter will just shift the binary output so that it fits with the -1 1, okay? And here you have the standard binary shifter, which provide a continuous action output, okay? So that's 1 and -1 as real numbers. And there is also a binary shifter discrete, which provides just -1 and 1 as integers, which are used for the environment which take integers as input, because Gym environment check that what you give it as action corresponds to what it is expecting. Okay. Finally, wrapper that uses some side effects. That's the perf writer wrapper. So the idea of this one is that it will behave exactly as a standard environment, but it will save into a file the state, the number of episodes and the total reward and the number of episodes and the duration into two different files. So then you just have to display performance from those files. And what's interesting is that, again, this part of the code is hidden, so you are just interacting with your environment without caring about saving anything, but it's saved into a file without having some code for that in your main loop. That's hidden in the wrapper itself. Okay. So, but there is a cost to pay with that particular approach, which is that when you are using the perf writer wrapper, you have to specify the file name in advance. So when you are just starting to use an environment, you have to specify this file name, and if you forget that, this won't work. Okay. And also you have the possibility to change some flag. If there are some runs where you want to save the performance and some runs where you don't want to save the performance, then you have to change these flags from true to false or the contrary. This is useful, for instance, in the case where you just want to see the performance we're evaluating and not when training. Then you have to put those flags to false when you are just training. Okay. And finally, the global picture is that in my labs, what I am doing is that when I am just calling a particular environment, I will just use this make-env function that, depending on the environment and the type of policy and the number of steps, etc., will build the particular environment with wrapper around this environment and wrapper around these wrappers, etc., so that it gives me the correct configuration so that my code will work whatever the environment name and policy type. Okay, so for instance, here I'm just making the environment the internal environment. So for instance, it will be cartpole, and then I will say that if this environment is discrete, then I will check that the policy is of the Bernoulli type, okay, because I cannot use Gaussian policy with discrete actions, okay. And for instance, if I am using cartpole or cartpole continuous, then I am using the feature inverter, where I am inverting feature 1 and feature 2, so that I can display the features I am interested in when I am using the cartpole. And for cartpole, I also need to call the action vector adapter, because cartpole will output, will take as input scalar as action, whereas my code will output a vector, so I will have to extract the scalar from the vector. And if my policy is a Bernoulli, then I have to use a binary shifter, depending on the discrete or continuous case. And okay, and this part will be useful for those who are doing the labs. If you want to use pendulum or mountain car continuous, you will have to tweak a few hyperparameters, and for that I have just designed a pendulum wrapper. This one does nothing, but there you can put whatever you want in the code, for instance to renormalize the reward, which is something that you will probably have to do during the labs. Finally, I am putting the perf writer around everything. I just print the environment so that you can see what you are using in practice, and then I return this external environment, which contains all the environments like onions. Okay. A different part is about visualizing policies. Okay, so those functions, okay, this front part is about visualization in general. So there is visualization, I can't remember exactly the name of the folder, which contain all the visualize functions. And the first case is policies. So for instance, here you have a policy for cart poll, the Bernoulli policy for cart poll, and here you have a normal policy for cart poll. Okay, and that's typically a case where I am using the feature inverter, because for cart poll my state is 4-dimensional, but I can only display 2 dimensions. So I have reversed the third and second features so that it shows me the position and the angle, and not the position and the position velocity. Okay, because those dimensions are more interesting than just using the position and its derivative, or the angle and its derivative. I don't remember. Okay. And what's interesting is that if you call those plot function that provides those kind of images, it can either do it interactively, so it displays you the picture during running the code, but it can also save a picture which is saved in data.plots. Okay. Something you have to know about visualization of policies is that there is a general let's say input function which takes the policy, the environment, etc., and depending on the observation size of the environment, it will call a different policy plotting function. So if it's 1-dimensional, it will call this one. If it's 2-dimensional, it's this one. And if it's n-dimensional, then it will call this one that does the same as this, but ignoring the additional dimensions beyond 2. Okay. There is exactly the same kind of things with visualizing critics. So this time what you see is the value of doing a particular action in a particular state. Again, that's cart poll. Okay, that's in Visu critics, and again you have a unique plot critic function to call all the different visualization function depending on the dimensionality of the state. Okay. You also have a function to visualize trajectories. So that's trajectories in cart poll, where you have the angle and the angle and the position, and you start from here, and you can see that along the trajectory the system converged towards the center. So this was a case where it was performing well, because finally you get stable here. Okay, and that's a visualization where with pendulum, where in fact if you use the position and your angle, all your data points should be around this ellipse. And you can see that the colors are changing along the trajectories. Okay. And finally, you have many functions to visualize results. So that's in visualresults.p. The corresponding results were saved when running the algorithm into data.save. So though the code of these functions just get files from those directories, and they will plot the corresponding pictures and also save them into data.results so that you can visualize them afterwards, and not interactively if you are just running the algorithms for a while. Okay. An important point that I will explain later on using the argument part is that those file name where I save the results, the file names are very, very long because they specify all the hyperparameters that were used to get the results from the run. So that's the last part about various things. So first thing is about hyperparameters. So one point is that hyperparameter tuning is critical in reinforcement learning, so it's a good idea to have code specific for that. And the idea is that these basic policy gradient labs can be used under various settings. So the idea is that the setting is put somewhere in a specific place so that you can change it easily. Okay, you need a flexible hyperparameter setting method, and this is what you will see on the next slide. Okay, but also one important point is that when you are calling the code, you can specify the hyperparameter setting that you want. Okay, so for instance, you can call Python policy gradient main. That's one of the main functions. You will see this afterwards. And then I specify that the hyperparameter of name takes as value pendulum v0. The parameter and number of cycles takes the value 100, etc., etc. If I don't specify the value, then it takes the default values which are set in arguments.p. Okay, and I want to say that this is a standard Python approach to specify hyperparameters or arguments for a program, and you should use those techniques when you are coding, particularly in machine learning. Okay, so let's have a look at the arguments.p file. So you need to have a method whose name is getArgs. Okay, and which uses an argument parser. So this is the class that will take this string and will parse the string of arguments so as to retrieve the value for all the arguments. And here you can see that I am adding arguments where I am specifying the name of the argument and then its default value. Okay, and you also have a help message. So if you do something that the getArg function does not understand, then it will display the help so that you can have an idea of what you should have done. Okay, so for instance, the default environment is cartpole continuous. The default policy type is Bernoulli. The default gradient kinds are you can use a vector with a sum, a discounted sum, and a normalize, etc., etc. Okay, the learning parameters, the default learning parameters values are gamma is 0.99, etc., etc. Okay, understood? And then for using this, you have to import the argparse classes, and in the main you will see how you call these arguments. Okay. A different thing that I wanted to say that's also a good practice is that given this list of arguments, I have defined functions to provide a string specifying all arguments and arguments value. So here I have the make study string that tells me what's the environment name, what's the study name, what's the critic update method, etc., etc. Then I have 3 different methods for local parts of the arguments, and then I have the make full string which calls each of those 3 methods so as to provide a very long string that tells me every hyperparameter that I used. Okay, so that's a good practice to do this. Okay, the general idea is that you want to save results into files where all the hyperparameters are specified, because when you go back to your folder and you open a particular curve or a particular display of results, and that's interesting, you would like to know what was the hyperparameter setting that you used. And if you forgot, that's lost. But if it's specified in the file name itself, then you know exactly what you did. Okay, that's why it's a good practice to do those kind of things. A few various things to finish. So let me say that you will find an algo class which is used to collect a few algorithm-related parameters and responsibilities so as to make the code a little clearer. Okay, that's algorithms that will call Critic training under various settings. So if you are not using critics, you are just using policy gradient with sum of reward, okay, no baseline, then you don't need this class. Okay, and by using this algo class, it allowed me to simplify the code of the simu class that you will see just on the next slide. And it contains the enumeration of many cases corresponding to these various settings. So the simu class corresponds to the main simulation of running an agent and training it in an environment. Okay, that's for running a simulation over a set of episodes. So it connects together the learning agent, its policy, its critic, and the environment. So that's the central class, let's say. And it can call for environment steps either for storing data in batches in the training context or just for measuring performance in the evaluation context, and the function names are straightforward. I won't show you the code, but just have a look at the simu class in the code. And then the global schedule of using this simulation class and evaluation episodes and etc. over different studies is in the main PG, main beta, main etc. files. Okay, so that's in the main files, the schedule itself. So those main functions, you have 4 of them. The main policy gradient is the one that you should use for your labs by default. Okay, that's the entry point to study policy gradient algorithms. You have the main regress, which is very similar to main policy gradient, but it uses regression to initialize a policy in the particular case of more continuous mountain car, where you need expect trajectories to initialize your policy, otherwise exploration won't work. There is the main beta case, which is used in a very specific context to evaluate the performance of a particular approach, which is called beta exponentiation. You should not care about this. And there is also the main end step case, which is probably not working at the moment, where I wanted to study the effect of end step return on those techniques, but I have not updated this code for a while, so probably it's broken at the moment. And that's it. So if you want to use this code and some points were not clear, of course, send me an email. And don't hesitate to ask questions. And if you want to participate on the code, etc., of course, also send me an email. Thank you for listening.